Well, hello, good people. Today I do have a short demonstration to show you. We are talking today about fluid mechanics and Bernoulli's principle. And here I have a hairdryer and a ping pong ball. And I'm going to turn this thing on and it's going to be loud, so you probably won't be able to hear me talking, so you're just going to have to watch. Here we go. Pretty fun. Now watch this one. Now the question is, while the hairdryer is running, especially when I turn it to the side, what allows that little golf ball to stay in the stream of air? Why doesn't it go falling out? And that has everything to do with Bernoulli's principle, our topic of the day. Let me pause real quick, get situated, and then we'll come back. One moment. Now the topics that we are going to discuss today, we're going to talk about two different properties of fluid mechanics. And these properties of fluid mechanics apply to what we call ideal fluids. An ideal fluid is a fluid that is incompressible, and non-viscous. Incompressible and non-viscous. I don't know why it's doing that thing where it's like, hello, this is what this video is. Okay. It applies to fluids that are incompressible and non-viscous. Let's start by defining each of these terms before we talk about the equations that we're going to apply to them today. First, incompressible. Incompressible means it can't be squished. It can't be compressed. This is something that we'll deal with today for ideal fluids. This is not every fluid is an ideal fluid. So when we say incompressible, we mean not like air. Air is not an ideal fluid. It is very compressible. So you can take some air, you can squish it down, you can compress it, you can make it take up less space. An ideal fluid is incompressible, meaning you can't squish it down to make it take up less space. Something like water, for example, we would say, well, you can't actually squish the water molecules together anymore to make it take up less space. If you squish it somewhere, then it gets squished everywhere and it's not going to get smaller. So an ideal fluid is incompressible. You can't compress it, you can't make it more squished. Next, we say that an ideal fluid is non-viscous. You know all about viscosity from your work in chemistry. If a fluid is very viscous, that means that the molecules really love to stick together. They love to hang out together. This would be in something like honey. Honey doesn't flow nice and quick. It flows very slowly. Why? Because each little molecule says, no, I'd like to be with that other little molecule, and they'd all kind of like to be together, and they all want to stick together. And so, because there's a lot of what we like to talk about this as internal friction within the fluid, as all the little molecules are trying to be buddies and trying to be next to each other, it makes it much harder for the fluid to flow. So we are looking at fluids that are incompressible and non-viscous today, and that's what it means to be an ideal fluid. Today we're going to talk about two different concepts under the broader topic of fluid mechanics. We are going to start by talking about what we call the continuity equation, or the equation of continuity. Wow, that does not look like the letter N. Continuity equation. We'll start by talking continuity equation, and then after that we will talk about Bernoulli's principle. Okay, let's start today with the continuity equation, or the equation of continuity. I'm going to start here by actually drawing a picture of your backyard garden hose. So I'm going to pause the video, I'll get a picture drawn up here, and then we'll talk about it. 1 second. Now, when you were a child, you knew how to be the most dreaded and fearsome creature in the whole backyard. You would take your hose And what you would do, my family was not very fancy gardeners. We like when we purchased the house that I grew up in, there was this beautiful, beautiful garden in the backyard, and within like 2 years there was no longer a beautiful, beautiful garden in the backyard because we were the worst at gardening. But we did have a backyard hose. We had a hose in the backyard. This hose, though, we didn't have any of the like fancy nozzles or like the fancy attachments. What you had, if you wanted to control the water that was coming out of the hose, is you had your thumb. And what you would do, you know how to do this, you know how to be the most fearsome creature in the whole backyard. All that you would have to do is, as the water's coming out of the hose, you put your thumb over the nozzle. And what you do when you put your thumb over the little opening there is then you prevent how much water is coming out, so it all comes out of a little bit of a smaller area. And then that, for some reason, makes the water far more fearsome. Let's talk a little bit about why that's true. It has everything to do with what we call the continuity equation. Now here I've drawn a hose, and this hose is very fancy because you see it has a fancy nozzle at the end that kind of streamlines things for you. So if you did not have to use your thumb, if you actually cared about gardening, then maybe you'd have a cool nozzle like this, but my family did not. We used our thumbs. Now, the continuity equation is basically an equation. It's basically a restatement of conservation of mass. So here's what it says. It says if you have a certain amount of fluid here that is passing through this space. Actually, I'm going to redraw it. Okay, yep. Final conclusion. I'm drawing it like this. Okay, if you have like some water, I'm imagining like water flowing through this whole thing, but I'm drawing just like a chunk of water here, but the water is flowing through this whole thing. If I have a certain amount of mass per time moving through this part of the hose, that means that I also have to have the same amount of mass per time leaving the hose on this end. So the amount of mass of water per time that's going this way has to be the same amount of mass per time that's going this way. Basically, it's a conservation of mass statement. The amount of mass per time on this side, we'll call this at area 1, has to equal the amount of mass per time on this side. Now, this should make some sense to you. If I put 7 drops of water into this end of the hose, you would expect to see 7 drops of water come out of this end of the hose. If I put 13 drops of water into this side of the hose, you would expect 13 drops of water to come out of this side of the hose. If I put 2 drops of water in this side of the hose, you would expect 2 drops of water to come out of this side of the hose. If I put in 3 drops of water over here and you saw 7 drops of water come out the other side, you would say, what? Where did that extra mass come from? That makes no sense. You can't just have water droplets appear out of nothing. Similarly, if I put in 7 droplets over here and 3 droplets came out on the other side, you would say, well, where did the droplets go? Where are the extra 4? You'd maybe look in here to see if they got stuck or something. It doesn't make sense that if you put in 3 droplets here, you would get out 7 on the other side, and it doesn't make sense that if you put in 7 here, you'd get out 3 on the other side. The equation of continuity is basically an equation of conservation of mass. It says however much matter you have over here, that going in on this side, that's how much matter you have to have coming out on this side. Now, here's where the continuity equation really gets interesting. Check it out. Do you see how here I have a much wider area, a much wider cross-sectional area of water, and here I have a much smaller cross-sectional area of water? If I looked at the water over here, if I wanted to talk about like, okay, how much water do I actually have? I could talk about, let me do this over here. Okay, there you go. Your patience is much appreciated. Okay, so here's what I could do. I could say, well, I actually don't really, like right now I didn't really give you much of a mass for the amount coming out on this side and the amount, the mass of the water on this side. But here's what we could do. We could say this section here has a cross-sectional area like this that we shall call A1. And this chunk of water here has a, we could talk about like the length, I suppose, of this chunk of water, or how far this chunk of water moves. We could say this chunk of water moves a distance of a little delta x1. That's how big this chunk of water is. Then we could talk about over here, this little chunk of water has a little cross-sectional area, A2, but it has a little distance here, a little length of delta x2. Hey, notice this should make some sense to you because we have to have the same amount of water over here as over here. Because I have a much bigger area over here, I have a much smaller width, and then because I have a much smaller area here, I have to have a much longer width in order for this amount to be the same as this amount. That should track with you, okay? Okay, now here's what we could say. I didn't actually give you the mass here, but we could talk in terms of rho v. You know from back in the day that density is equal to mass over volume, and sometimes if I don't give you the mass, then you can rearrange and find the mass by saying that the mass is equal to the density times the volume. Well, we could talk about the mass over here on this end by doing the density of this water times the volume of this water divided by delta T. And over here, we have the mass of this water over here times the density of that water over there times the volume of this water over here. Oh gosh, I should probably, now that I put hats on one, I should probably put hats on both. Divided by the amount of time. Oh no, not squared. Come on, do better. Okay, good. So this shows us two expressions for what we just said. It's the mass per time for both sides, except we translated it into, density and volume. Now looking at this picture, we know that this is a little cylinder, and if I wanted to find the area here, or if I wanted to find the volume, I would do area of the base times the height of this little cylinder. And then over here, I could do the same thing. I'd do area of the base here times the length of this cylinder, which is delta x2. I'm really struggling with my subscript on that guy. Okay, now here's what I want you to see next. First, the density of the water on this side is the same as the density of the water on this side because they're both water and this is an ideal fluid, meaning it's incompressible. So you can't squish it down so that this side has more density and this side has less density or vice versa. No, the density in one place is going to be the same as the density everywhere else. So I can cancel out the densities on either side because the density of water is the density of water, whether it's on this side of the hose or this side of the hose. Now here's what I want you to see next. Do you see how here I have a delta x over a delta t? I tried to highlight that, but it didn't really highlight at all. So don't use white chalk for your highlighting, folks. We can let's use a light blue, which, no, because that's going to match the color. That's going to be bad news. We'll use yellow because that's a highlighter color, but then we got to make it more chill because right now it's so very not chill. Let's make it more chill. Yeah. Okay. Okay, do you see that right here? I have a delta x over a delta t. And do you see that right here? I also have a delta x over a delta t. Well, you know what delta x over delta t is, folks. You've known it like practically your whole life at this point. A delta x over a delta t is v. We're talking about the speed of the water. If the water can move this distance in a certain amount of time, or this distance in a certain amount of time, that's how fast the water is going. So we can write this as A1 V1, where this is the area of the water here, and this is the speed of the water here, is equal to A2 V2, where this is the area of the water here and the speed of the water here. And this is our official equation for the continuity equation. Is A1 V1 equals A2 V2. Yes, of course, do add it to your bag of tricks. It is most certainly worthy. Now, check the implications of this equation really quick and make sure that the implications make sense to you. It says when the area is bigger, the water doesn't have to move as fast, but then if the area gets smaller, then the water has to move faster. Doesn't that make sense with our whole idea of conservation of mass or conservation of matter? If you are trying to get 5 drops through this way in the same amount of time as you need 5 drops through this way, but this one's a much smaller area, then it has to flow faster to get 5 drops out of here in the same amount of time that it took 5 drops to go through here. So we can see that really this is just a restatement of conservation of mass. If you have a bigger area, the water moves slower, but then when the area narrows down, the water has to move faster in order to get the same amount of mass to move through in the same amount of time. You experience this when you put your thumb over the hose. What happens is the water flows slowly through the hose, then you constrict the area, you make that water go out of a teeny tiny area, and when it has to go out of a teeny tiny area, it comes out going much faster. And so when the water narrows, when the cross-sectional area narrows for where a ideal fluid is flowing through, then it'll flow a lot faster. I do have one other thing to show you. Let me see if I can move my computer over there safely. One moment, please. Hello, welcome to my sink. Okay, now I want to show you something, and this is something that you might see much better at home. So you should definitely, this is definitely something that you should go home and try this, and something that you may have noticed before. But what you'll see, and I will talk to you first, and then I'll turn the sink on because the sink gets pretty loud. But what you'll see is as this water flows out of the spout, the water starts out wider up here at the top, and then it gets skinnier and skinnier and skinnier as it falls. Why is that? The continuity equation. Well, you know how we said that if you constrict the area, then constricting the area will make it go faster. But it goes the other way too. If it goes faster, then it'll take up less cross-sectional area. Why? Because you have to have the same amount of mass. If you're going much faster, well then you're going to thin out a little bit because there's not enough stuff to go fast and to stay really wide. So what you're going to see here, I'll turn this on. This really only works for when you have the water acting as an ideal fluid. So what I'm talking about when we're acting as an ideal fluid, you're going to see that an ideal fluid looks like when the water is nice and clear. You know how you could run it really fast and it would be kind of white and foamy and bubbly? That's not an ideal fluid situation. It's when that thing looks like a nice clear rod. And again, this is going to be, you're going to be able to do this even better at your sink at home than we're going to be able to do it here. But I'll turn it on, and what you'll see is it'll be fatter up at the top. Then as it falls, it gets faster, 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 faster. When it gets faster, V2 is bigger, so A2 has to be smaller. Check it out. Okay. Do you see this here? I don't know how well you can even see this at all. It's fatter up at the top, it gets skinnier down at the bottom. Definitely something to try at home. Okay, in 1 second we're going to transition back over. Okay, now, whoops, I forgot to plug in my computer. That could have been dangerous. Now, a few quick conceptual checks to check in and make sure that you're understanding things. First, suppose that you have a river that is flowing. And suppose that you go to a part of the stream where the water, or where the stream gets narrower. Does the stream flow faster, slower, or the same speed? Suppose that then you go to a section of the river where the river then is a little bit wider. Does the water flow slower, faster, same speed? You know, based on experience, you go to the narrower part of the river, and doesn't the water flow so much faster? Isn't the water flowing way faster in the narrower part of the stream than in the wider part of the stream? In the wider part of the stream, you'll watch it kind of trickle along a lot slower. When the stream narrows down, it goes a whole lot faster. Continuity equation here. Wait, let me move my face out of the way. Classic. If you decrease the area, then your speed will increase in order to make sure that these are the same. If you increase your area, then the speed will decrease in order to make sure both sides of the equation stay the same. One other question is, same thing happens with a syringe. Why does the fluid flow faster out of the end of the syringe than out of the top part of the syringe? You push down nice and slow on the top part of the syringe, and it comes out way faster on the bottom part of the syringe. Why? Because your area gets smaller, and if your area gets smaller, it's got to go a little bit faster. Next, we're going to go ahead and get a little practice problem pulled up. You can go ahead and take out your textbook. This is on page 286, question number 1. I have my textbook here. Let's get a little new, not that. Let's get a new drawing going here. If it'll load, it can do it. I believe. Okay, here we go. This is going to be page 286. We're taking a look at question number 1 together here today. Okay, here we go. Page 286, question number 1. Here's what it says. This is in the little section review box down here at the bottom. It says, water at a pressure of 3.00 times 10 to the 5th pascals flows through a horizontal pipe at a speed of 1.0 meters per second. The pipe narrows to 1/4 its original diameter. What is the speed of the flow in the narrow section? Okay, let's take a look here. You have water that is flowing through this section here, and then it's going to narrow down to 1/4 of the original diameter. So if we originally had a diameter here of D, then the diameter here is going to be 1/4 of D. The question is, if the water starts by flowing with an initial speed over here of 1.00 meters per second when the diameter is D1, what will the speed of the water be over here when the second diameter, D2, is equal to 1/4 of D1. It also gave us the pressure of the water in this section of the pipe. It says that the pressure of the water here is 3.00 times 10 to the 5th pascals. Okay, let's go ahead and see what we can do here. I am going to start by starting with the continuity equation, because I say that the area of the first cross-sectional area times the speed of the water in that section is going to equal the area of the second cross-sectional area times the speed of the water in that section. Now, here's the thing. I'm looking for V2, so I can rearrange this guy here to find V2. When I rearrange to find V2, I get A1V1 all over A2. Next, I can plug in some formulas for the areas. I wasn't given the area, but I was given the diameter. So the area of the first cross-sectional thing would be something like pi times d over 2 squared. Notice that I don't say pi r squared because I wasn't given r, I was given d. So this is going to be pi d1 over 2 squared times v1 divided by pi d2 over 2 squared. Whoa, I was about to say times v2, but that would be crazy since I already pulled out my v2. Go away, v. Okay, perfect. Now, check it out. My pi will cancel out here, and this will become a 1/4, and this will become a 1/4. So my 1/4s will actually cancel out with each other, and I will be left with an expression that looks kind of something like this. I'll have d1 squared v1 all over d2 squared. Now, I can plug in what I have for d1 and d2. For d1, I just have d1 squared. For d2, I don't know what d2 is specifically, but I know that it's 1/4 d1. Now check it out. Sorry, we'll loop back around up here and continue our work. This is going to be a d1 squared v1 over that's going to be a 1/4 squared, which is a 1/16 d1 squared. Hey, notice my d1s will cancel out, and then I have a 1 over 16th in the denominator, which is the same as a 16 in the numerator. So I get that v2 is 16 times v1, and v1 is 1.00 meters per second, so v2 is equal to 16.0 meters per second. And there it is. There is a little practice problem with the continuity equation. Notice the pressure was actually not even relevant at all. We didn't have to do anything with the pressure at all. And yeah, it was just given to us for fun. Okay. Next, we are going to talk a little bit about Bernoulli's principle. Let's make our way back over to this original page. We have completed our discussion of the continuity equation, and what we'll talk about next is Bernoulli's principle. I'm going to say, check, continuity equation is done. Let's talk about Bernoulli's principle. Now, here's a question, and here's a place where you could most certainly have some financial gain by asking this question, because most people will get this question wrong. If I asked you, where does the water experience more pressure? In the tube of the hose or coming out of the nozzle of the hose? Which one is a more pressureful situation? Most people would say coming out of the nozzle of the hose is when it experiences more pressure. But that's not quite true. You'll remember that pressure is force over area. And velocity, or speed, is distance, that says distance, by the way, over time. If the water coming out here of this nozzle experienced both more speed, because we know it's coming out faster, continuity equation, if it experienced both more speed and more pressure, then it would have to experience more distance per time and also more force. And we know that force times distance is work. So if you had more water coming out faster if you had water coming out faster with more distance and with greater pressure, more force, you'd have more work, which means you would have just invented some energy. You would have more energy coming out of the nozzle than you did before the nozzle. And if that were the case, then everyone should be investing in nozzles, and you should make nozzles your primary investment, because we just came up with a way to invent energy using the nozzle. Unfortunately, though, this is not correct. On the contrary, we say, and this is what Bernoulli's principle is, I'll write it out for you, as the velocity of a fluid increases, the internal pressure of the fluid decreases. As the velocity of a fluid increases, the internal pressure of that fluid decreases. Let me go ahead. I'm going to grab another page, actually, and write this out 1 second. Okay, here we go. As the velocity of a fluid increases, the internal pressure of the water decreases. Now, we have to be careful by what we mean about internal pressure. By internal pressure, what I do not mean is how hard those little water molecules are hitting your hand. Water molecules? Water droplets is what I really mean. How hard those water droplets are slamming into your hand when they come out of the hose. What I'm talking about is how much pressure does that fluid put on the walls of its container. When a fluid moves faster, it puts less pressure on the walls of its container. Let me show you. Here I have a hose, and here I have some water droplets inside of that hose. Okay, here I also have a hose, and here I have some water droplets inside of that hose. Okay, now suppose that, I don't know why these ones got more aggressive. Suppose that these water droplets are kind of moving slow. They're all kind of meandering their way along. They're all kind of going like this, and some are going like this, and some go like this, and they're all kind of generally moving this direction, but they're all just kind of meandering along. If they're all meandering along like this, well, a lot of them, as they kind of meander, they're going to kind of bump around a little bit. They're going to run into the walls of their container just a little bit more often because everybody's just kind of meandering. And so we're all generally going in the right direction, but as we kind of meander along, there's going to be a lot of bumping into the walls. But when these water molecules are flowing very fast, here's our slow situation. When these water molecules are flowing, slow with an extra swoop on the W. When these water molecules are flowing very fast, everyone has an objective. We are all going this way. They are marching steadily like soldiers on a mission, and everyone is moving this way together. And so everybody goes this way, goes this way, goes this way, which means they aren't bumping into the walls as much. They don't have time to bump into the walls as much. They have a direction. They have a mission. They have a purpose. And since everybody is going this way, well, then there's less hitting on the walls. When we talk about internal pressure, we're talking about how hard are the water molecules or fluid molecules hitting on the walls of their container. And when they're going slow and they're just kind of ambling about, well, then they might run into the walls of their container more often, so it creates more pressure. But when they're going much faster, they are all on mission, they run into the walls way less. And so that's kind of the reasoning why we see that as the velocity of a fluid increases, the internal pressure, how often those water molecules are hitting on the walls of their container, that decreases. Quick pause here. Can you explain to yourself, why is Bernoulli's principle what it is? Why do we say that as the velocity of a fluid increases, the internal pressure of that water decreases? And then we'll go through a few examples. 1 second here. Okay. So I have one example that I want to take a look at. Oh my GOSH. I just realized that this is of the water decreases, but earlier I said fluid, and that doesn't make any sense. It's as the velocity of a fluid increases, the internal pressure of the fluid decreases. Otherwise, that is just like, I mean, it's fine. It's just kind of inconsistent. Let's go ahead and fix that here. Sorry, just testing your eraser capabilities. Okay. That's what Bernoulli's principle says. As the velocity of a fluid increases, the internal pressure of the fluid decreases. And I wanted to show you an example here. So here I have some slips of paper. One of them has some physics equations written on it, which is super fun and just makes it an even more fun piece of paper. Okay, now here's what I'm going to do is I'm going to hold both of these up next to my face like this, and then I'm going to blow between the two pieces of paper. And the question is, when I blow between the two pieces of paper, which way will they go? Well, when I blow between them, watch what happens. You can see that the two pieces of paper move together. Now, why do these two pieces of paper move together? Well, because when I blow, I create some fast-moving air. And that fast-moving air has a lower pressure, meaning it presses on the pieces of paper less hard. Meanwhile, on the outsides over here, I got slow-moving air here and slow-moving air here. That slow-moving air is very high-pressure air, so it presses on the paper a little bit harder, and the air on this side also presses on the paper a little bit harder. So you got high-pressure air here, high-pressure air here, low-pressure air between them because it's moving fast, and between high pressure and low pressure, if you got high pressure pushing you this way and low pressure pushing you this way between those two, well, then the high pressure is going to win, and it pushes them both towards each other. So that's what we see. That's a great example of Bernoulli's principle, that you see that these two things, once you have a faster moving fluid between them, it drops the pressure and the higher pressure wins over the lower pressure. Now, you've also seen this example before, like when you're in your car and you're sitting in your car and you put on your blinker to turn left, and you're sitting in your car and you put on your left hand turn blinker and you're watching and you're waiting for that little arrow to turn green. And as you're waiting, all of a sudden a car comes zooming past you, going very, very fast, and you feel your whole car go boom, boom. You know what I'm talking about? You know when this happens to you? Why is that? Well, because as that car goes flying past you, that car going flying past you has a whole lot of speed. It's going very, very fast. And because it's going very, very fast, well, then it makes the air next to it also move very, very fast. So you got fast-moving air going next to you on this side. So you got fast-moving air going next to you on this side. And if you got fast-moving air going next to you on this side, that fast-moving air is very low pressure. Meanwhile, next to you on the other side of your car, you got nothing happening over there. You got nice still air. So the air is nice and still. That's high pressure air. Over here you got air moving fast. That's low pressure air. And the high pressure air will push you towards the low pressure air. And so your whole car will go boom as you kind of rock back and forth like that. You've also seen before, as a truck is going zooming down the highway, I'm thinking about one of those big trucks with the tarps over the back. Now when the truck is totally stopped, then the tarp on the back of the truck sits nice and flat. But then when the car starts going, when that truck starts going really, really fast down the highway, then all of a sudden you'll watch and that tarp will kind of billow upwards. It'll kind of balloon upwards. And I always thought, what is happening there? Why does it go upwards? Well, here's why. In the bed of the truck, you got still moving air. You have still not moving air. That's very high pressure air that's sitting in the back of the truck. Meanwhile, outside the truck, because the truck is moving very, very fast, then outside the truck, you got very fast moving air moving over the top of the tarp. So you got fast moving air over the top, that's very low pressure. Slow moving air underneath the tarp, that's very high pressure. High pressure wins over low pressure, and it pushes the whole tarp up, and the whole tarp balloons upwards. We got tons of other examples of this kind of thing too. Hey, at the beginning of this video today, I showed you an example with a hairdryer. And I would take that hairdryer, and when I would move it and I would tip it to the side, that ping pong ball, it wouldn't go flying off. No, the ping pong ball stayed right above the hairdryer. Why? Well, because the hairdryer creates some fast-moving air. That fast-moving air is low pressure. Meanwhile, on the outsides of the fast-moving air, you got still air. That still air is low pressure. So you got, oh, whoa, sorry, still air is high pressure. So you got high pressure air on the outsides, low pressure air on the inside. The ping pong ball, it would like to leave because gravity is pulling it down, but when it tries to leave, there's some high pressure air right here pushing it back up towards the low pressure air. And so that ping pong ball will stay in that low pressure pocket instead of falling out. Lots of other examples too. My cousins they used to all live in Oklahoma. You've heard about this before, how that's where the church gym was, and so we'd all go to Oklahoma to roller skate and that kind of thing. But and in Oklahoma, they know about tornadoes, man. They live in Tornado Alley. And so all of my cousins know that if a tornado goes rolling through your neighborhood, a lot of times the windows of your house will blow out. And what I mean is blow out. They literally explode outwards. Now the question is, when a tornado goes rolling through your neighborhood, why do your windows burst outwards? Well, because of Bernoulli's principle. You got some really fast-moving air going right outside your window because you got a tornado, you got super, super high winds. Fast-moving air right outside your window. Inside your house, the air is nice and still. Maybe you got the air conditioning running or something like that, but you got really still air inside your house. Still air is high pressure. Outside air is low pressure. And so that high pressure pushes against your windows, and it will literally break your windows because the pressure on the inside is so much bigger than the pressure on the outside. We have other examples too. Did you know that all the prairie dogs in the world know about Bernoulli's principle? Did you know this, that they all teach it to each other? All the prairie dogs in the world know all about Bernoulli's principle, and they all teach it to each other one by one. The little baby prairie dogs, when they're born, they're not born knowing about Bernoulli's principle. You think a baby prairie dog wakes up in the world and says, "Oh yes, I know about Bernoulli's principle now." No, that's not what happens. What happens is the older prairie dogs must teach the baby prairie dogs about Bernoulli's principle. And so when the baby prairie dogs are of age, then the older prairie dogs, the father prairie dogs, bring their son prairie dogs outside, and they have like a whole like Mufasa Simba moment where they're like, "Look out over the land, and do you see that everything the light touches is ours?" And the baby prairie dog goes, "Uh-huh." And then he says, "And now you shall also learn Bernoulli's principle." And the baby prairie dog says, "Oh yes, teach me Bernoulli's principle, father. Thank you so much for educating me so that I can stay alive and have a nice, happy, long life." And the grown-up prairie dog says, "Why, yes, you're very welcome, son. I would just hope the best for you." And so here's what he teaches them. He says, "Baby prairie dog, you must know about Bernoulli's principle. Otherwise, you will not build your home correctly, and you will die." Have you seen before that when prairie dogs build their homes, they got different entrance styles? Oh, that's not very good. They got different entrance styles. You got some entrances that look like this. And you got other entrances to their homes that look kind of like this. They look kind of down like a little hole in the ground like this. And so you got some entrances up at the top like this, kind of like volcano style entrances, and then you have like deep in the hole style entrances. And then, let me move this guy out of the way. Bow, 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 bow. Get up here. Yes, perfect. And then you'll have like a bunch of tunnels underground connecting them. So you'll have like a tunnel. Oh gosh. Oh gosh. Oh gosh. Oh my. Please cancel. Please don't do that. Okay. Oh gosh, then I just made a God. Ah! Boop, boop, boop. Ba-doop. Wow, that was almost a crisis. Good thing we stayed calm. Am I right or am I right? Okay, so you've got some tunnels connecting these entrances here under the ground. And now down here, down below, like this home bar where you got like my Chrome kind of stuff going on in my files and that kind of stuff. Down here is where all the little prairie dogs, that's like their little home. That's where they have like their bedroom is over here and their little kitchen is over here. And this is like where their little dining room table is. And what happens is all the prairie dogs will sit underneath there. And when they have their breakfast in the morning, they'll all sit at the dining room table and they'll all breathe as prairie dogs do. And they breathe in and breathe out. And when they breathe in O2. And when they breathe out CO2. And then they breathe in O2. And then they breathe out CO2. And then they breathe in O2. And they breathe out CO2. Now, if they kept doing that forever in their little tunnel, then eventually they would breathe in all the O2 and they would breathe out CO2. And then there would be no more O2 to breathe in. And then they would stop breathing. And that would be the end of the prairie dogs. So, in order for the prairie dogs to stay alive, the prairie dogs have to have airflow happening in their tunnels. They have to get air circulation. That way, oh gosh, they have to have air circulation. If they have good air circulation going through here, well, then they'll get some air cycling in so then they can have more oxygen so then they can all breathe. So here's what the dad prairie dog teaches to the baby prairie dog. The dad prairie dog says you build one of your entrances as a volcano and you build the other one as a hole in the ground. And here's why you do that. Because on a windy day, the wind will blow. And when the wind blows across the plain, it'll blow like this. And then, as the wind blows, the moving air creates low pressure air. So you get low pressure air right over the top of your volcano. But for your entrance that's down here, like a little hole in the ground, for your entrance that's down here, there is a little pocket of air here that is protected from the wind. Notice the wind will pass over the pocket, but the wind will rarely dive down into the pocket. And so you get a little pocket here of still air. And if you have still air right here, that's high pressure air. So you got high pressure air here, low pressure air here, and the high pressure air will push air from the high pressure spot through the tunnel back over to, whoa, not like that. Oh my, sorry, my undo button is blocked, which is just dangerous stuff over here. Okay, 1 second here, undo, and pretend those lines connect even though they don't, and that's embarrassing. So it will push the high pressure air over here, high pressure, will push the air from here over to the low pressure air over here. And you'll get air circulation for all of the little prairie dogs. Now, this is something that they have to teach each other. Like, prairie dogs aren't born knowing about Bernoulli's principle. And if there is no adult prairie dog to teach them how to build their homes and to teach them about Bernoulli's principle, they won't build their homes this way. And then they don't survive. And it's so tragic. But just like you, prairie dogs are born uneducated, and then they are educated so that they live fuller and happier lives. The last thing that Bernoulli's principle is most famous for is Bernoulli's principle is famous for making the airplanes fly. When we create airplane wings, if you look at a side view of an airplane wing, I guess we'll go gray because that's what color I would build an airplane if I built it out of metal. So, airplane wings, if you look at them, they're not just like flat like this. Like, that is not what an airplane wing looks like. If you were to look at it from a side view, it's not just like a hunk of metal in the sky. No, that's not what it looks like. Boop. An airplane wing is shaped a little bit more like, did I do it? No, I did it really very, very bad. It's shaped a little bit more like, that is pretty good. It's shaped a little bit more like this from the side. Like, if you're looking at it as a side view, if you're looking at that wing head on, then this is what you're going to see. This is what you're going to see. So, here's what happens. What happens is the shape of the airplane wing forces the air that's incoming as it's like making its way through the air. It forces the air that's coming to choose to either go over the top like this or to go over the bottom like this. Now the shape of the wing makes it so that the air that kind of flows over the top like this ends up being very, I am not drawing this well. Your textbook has a much better picture. But it ends up being very fast moving air. Meanwhile, the air that drops down here ends up being very slow moving air, which means you get slow-moving air down here. Slow-moving air is high-pressure air. Up at the top, you have low-pressure air. And so the low-pressure air, because it's very fast-moving, competes with the high-pressure air, and the high-pressure air wins. And so even though both are pushing down on the wing, the high-pressure air pushes much harder than the low-pressure air, and the net result is lift. This thing gets lifted or pushed up towards the sky, and we call that force the force of lift. And that's probably one of the things that Bernoulli's equation is most famous for, is for lift on airplanes. And that, ladies and gentlemen, is pretty much all of Bernoulli's principle. We talked about two concepts today, both under the broad category of fluid mechanics, which is what happens when fluids move. We talked about the continuity equation, which says that the amount of area times the volume for one section of a fluid in a container has to equal the area. Whoa, back up, because I totally misspoke. Don't listen to me and don't let me confuse my V's. The amount of area times the speed of the fluid flowing through one section of a container or something has to equal the area times the speed for the fluid flowing through another section of the container. That's basically the law of conservation of mass. Then after that, we talked about Bernoulli's principle, which says that as the fluid of a velocity increases, the internal pressure of that fluid decreases. And we looked at quite a few examples. We talked about what happens when you're in the left-hand turn lane. We talked about what happens when you blow between two pieces of paper. We talked about what happens with the prairie dogs, what happens to the truck beds, and what happens to the airplanes. We talked about what happens when a tornado goes rolling through your neighborhood. And that is pretty much all for today, class. I hope you do have a wonderful rest of your day, and I will see you all next time. Bye, good people.